All right, so now we have talked about how we multiply complex numbers, right, in the Cartesian form. So if I give you x plus iy and u plus iv, you know how to multiply those complex numbers. What we would next like to understand is how do we multiply complex numbers when they're given in their polar form. So remember, we said we just represented cosine theta plus I sine theta as e to the I theta. We do not know their exponentials yet. Right? So we have not verified that yet so far. But exponentials have nice properties, right? That involve when you multiply stuff, right? There's nice properties that we associate with exponential. And what we would like to do is we would like to see if these we can use these properties when we're doing products for complex numbers. Right? And turns out we can, and that's what we're going to verify here first, is if I give you two numbers, z, which is r e to the I theta, and w, which is r e to the I phi, if I take the product of these two, I'm going to get the product of the radiuses, which is r times uppercase R. And what happens to the exponential here? We get e to the I theta plus phi. All right, so this is theta here. This is phi. All right, so let's go ahead and verify this. So we have z times w. Remember, z is r cosine theta plus I r sine theta times, and w is r cosine of phi plus r sine of phi. And let's go ahead and multiply these two. Sorry, there's an I missing there. So now we know how to multiply complex numbers in this form here, right? So in this case here, I'm going to get r cosine theta plus r cosine of phi, r cosine theta times r cosine of phi plus minus, I'm not having a good day, r sine of theta times r sine of phi. So that is the real part of our product, plus I, and now we're going to take r sine of theta, r cosine of phi, plus r cosine of theta, r sine of phi. All right, so that's what happens when we multiply two complex numbers in this form here. So now let's see, in all of these terms here, we get a lowercase r and a capital R, right? So I'm going to factor those out. So I'm going to get r times r. So what I'm left with is cosine of theta times cosine of phi minus sine of theta sine of phi plus I, and I'm left with sine of theta cosine of phi plus cosine of theta sine of phi. Right? And if we were to go ahead and Google trigonometric identities, these would be one of the important ones here. This here would be cosine of theta plus phi plus I, and that's an identity for sine of theta plus phi. And now we have cosine of an angle plus I sine of the same angle, which we can denote by e to the I, exactly that angle, which is theta plus phi, and that's what we wanted. All right, so without using property of exponential, which we have not established yet, what we can do is if e to the I theta is cosine theta plus I sine theta, we can say that if I multiply e to the I theta times e to the I phi, the angles just add. And that's going to be very useful for us. That interpretation is going to be very handy for us moving forward. All right, so what we're now going to look at is we're going to look at a few examples here. All right, so first, what we're going to do is we're going to look at this equation here, which says argument of I times z is equal to pi over 3. And what we'd like to do is we'd like to write z in terms of r and theta. All right, so let's start with, have I mentioned this here? So I don't know if I ever mentioned this, and that's if I did not, sorry. So if we take polar representation of a complex numbers, so if I have z is equal to r e to the I theta, remember r was exactly the modulus, and this theta here is what we call the argument of z. So this theta here is an argument of z. So I don't know if I mentioned this in the previous video. If I did not, that's what arg stands for. All right. So with that explained here, what we're given is we're given that argument of z, I times z, I times z is equal to pi over 3. What that means is if I want to write it, I can say I times z is, well, we don't know what the modulus of iz is, so let's just call it r for right now. But we know what the argument is, right? It's pi over 3, so this becomes e to the I pi over 3. All right, so if argument of I times z is equal to pi over 3, I can say iz is going to be some number r times e to the I pi over 3. All right, so now what I'd like to do is I'd like to find what z is. All right, so let's say I want to get rid of z here. Sorry, I'd like to get rid of the I here. What would I need to do if I want to get rid of I? Remember, I squared is equal to -1, right? So if I get I squared over here, I'd be left with -1. If I wanted +1, I'd want negative I squared on the left-hand side, right? So if I already have I here, and if I want 1 here, I'm going to multiply both sides by negative I. Negative I r e to the I pi over 3. Right? And if I do this here, negative I times I is going to be 1, so I get z is equal to negative I r e to the I pi over 3. All right, so now let's look at negative I. Right, so if I just look at negative I, the number, that I can view as 0 plus -1 times I, right? Which means its x-coordinate is 0 and its y-coordinate is -1, so negative I is right here. All right, so a question for you all is, if I know this picture here, can I express negative I in terms of, what is negative I in terms of r e to the I theta? Well, r, remember, is the distance from the origin, so r is going to be 1, and theta is the angle this line here makes with the polar axis, so that's pi over 2, that's pi, and that's 3 pi over 2, so negative I can be written as e to the 3 pi over 2. So what that means in this particular example is z is equal to 1 e to the 3 pi over 2 times r e to the I pi over 3. And from our previous example, we know that if we want to multiply two numbers in polar forms, we're going to multiply the modulus of it, or the r, so I get 1 times r e to the I, and now the angles get added, so I get pi over 3 pi over 2 plus pi over 3. When I do that, I get r e to the I, and that's 11 pi over 6. All right, so that's just, again, some getting you familiar with some sort of arithmetic involving arguments and polar representation of complex numbers. All right, so again, that's the purpose of this example here. All right, finally, equipped with what we know, we are finally going to introduce the DeMoivre's theorem. I should look up how to pronounce his name. All right, and what this says is that for any theta in R, if I want to take the nth power of cosine theta plus I sine theta, and that is going to be cosine of n theta plus I sine of n theta for integers n. All right, so let's just do n a positive integer. Alright, so and here's the rough idea of the proof. I know this video is already a little too long. So let's say let's just look at let's say z is equal to r e to the I phi. So if I want to look at z squared would be r e to the I phi times r e to the I phi, and we know how to multiply these. We multiply r times r, so it's r squared e to the I, and phi plus phi, which is going to be 2 phi. Alright, so if that's the idea, we can go ahead and show by induction. Alright, so by induction that z to the n is going to be rn e to the I n. Right, so in particular, when r is equal to 1, z to the n is going to equal e to the I n phi. So let's say z is equal to cosine theta plus I sine theta. That's exactly when r is equal to 1. So from here, I get cosine theta plus I sine theta to the n is going to equal e to the I n theta. And remember, by definition of exponential, that's going to be cosine of n theta plus I sine of n theta, which is exactly what we wanted to show. Right, so in this particular case here, what we're saying is if I take cosine theta plus I sine theta and I raise it to the power n, that's equivalent to just taking our cosine and multiplying the angles by n, and for the same for n. And we're going to use this a decent amount in class when we're talking about roots of unity. Right, so that's where I'm going to stop.